Hey everyone, and welcome to This Explainer. Today, we're diving into a genuinely fascinating everyday mystery. Why in the world do foam shoes dramatically shrink when left out in the sun? Seriously, if you've ever left your favorite, super comfortable clogs out on the porch on a scorching summer day and come back to find them seemingly sized for the toddler, well, you know exactly what I'm talking about. We are going to unpack the thermodynamic mechanisms behind heat-induced polyolefin footwear shrinkage. I know, it sounds super complex, but we're going to break down the data and the research step by step and solve this scientific puzzle together.
Take a look at the difference here. We've got a normal shoe on one side and this dramatically smaller, shrunken version on the other. It's basically our scientific crime scene. Now, both of these started out as the exact same size. They're made from identical materials, specifically polyolefins like ethylene vinyl acetate, which we usually just call EVA, or proprietary blends like Croslite. But clearly, something radical has happened to the smaller one after it was exposed to intense solar heat. The physical distortion is absolutely undeniable, but it really begs a massive question about the physics at play here.
Right? How did this happen? How does a solid, wearable object just reduce its overall footprint so drastically by simply sitting in the sun? To figure this out, we've got to look past the surface of the shoe. We need to investigate the actual molecular structure of the material itself and dig into what the research tells us about heat, stress, and polymers.
Let's get right into it with Section 1, Debunking the Dehydration Myth.
You know, when we see something shrivel up in the sun, our minds naturally jump to a familiar conclusion. It's like a grape turning into a raisin, or a wet sponge drying up on the kitchen counter. Because of those everyday examples, it's super common to assume the intense solar heat simply dried out the shoe, right? Like it evaporated some internal moisture and caused it to shrivel. But the source material definitively confirms this is not the case at all. There's literally no moisture evaporating from your EVA footwear to make it smaller. The shrinkage has absolutely nothing to do with dehydration, so we can officially cross that theory right off our list. And this brings us to a really brilliant scientific paradox. Basic physics teaches us that normal materials generally expand when they get hot. Think about metal train tracks on a blistering day, or the liquid inside a thermometer rising up. Heat adds energy, the molecules move further apart, and the material expands. It's Science 101. But footwear made of EVA, it does the exact opposite. When exposed to intense solar heat, it actually contracts. It gets smaller. It is a complete reversal of everything we'd expect from standard thermodynamics.
Which brings us to Section 2, the science of entropic elasticity.
Okay, so if it isn't dehydration and it completely defies standard thermal expansion, what exactly is making the shoe shrink? Well, the answer lies in a really fascinating principle of polymer science. The true culprit here is something called entropic elasticity. Let's break that down. EVA material is made up of these long polymer chains. During the lifespan of the shoe, if those chains are stretched out, they're essentially forced into a highly ordered, unnatural state. But in thermodynamics, systems naturally prefer chaos. They prefer entropy. So entropic elasticity is this process where those stretched polymer chains are desperately seeking to return to their natural, highly disordered, tangled-up state. They just want to curl back up, and the heat provides the exact energy they need to pull it off.
We can see this principle perfectly summed up here. As highlighted by Digital Insight founder Habtom Shnash-Abrha, the sun's heat acts as a trigger. The material is totally stable under normal, everyday conditions, but intense solar heat pushes the EVA material past what is known as its viscoelastic softening threshold. Essentially, the intense heat softens the physical bonds holding those stretched chains in place, suddenly giving them the freedom they need to move.
Now here's the kicker. Crossing this softening threshold triggers what researchers call a one-way shape memory effect. Once those bonds soften up, entropic elasticity completely takes over the steering wheel. The polymers remember their original chaotic compacted state, and they violently snap back into it. And because this effect is one way, the shoe rapidly shrinks in size and, spoiler alert, it will not just naturally cool down and expand back to normal on its own. The thermodynamic reaction has permanently altered its physical state.
Let's move on to Section 3, Manufacturing Stress Unleashed.
You might be wondering, why do these polymer chains want to shrink in the first place? Why are they all stretched out and waiting to snap back? The motive actually lies all the way back on the factory floor. The core issue is manufacturing-induced internal stress. When these shoes are first molded and produced, the whole process forces those polymer chains into a stretched, elongated shape to form the design of the shoe. This essentially turns the footwear into a loaded spring. The macromolecular thermodynamic reactions we just talked about, those are just the final step.
The shoe actually leaves the factory packed with internal stress, with all those stretched polymer chains trapped in an ordered state, just waiting for enough heat to release them back into absolute disorder.
Which leads us to our final section, Section 4, reversing the contraction process.
So, seeing as this shape memory effect is a one-way street under normal conditions, is the shoe just ruined forever once it shrinks? Can we solve this case and restore our footwear? Thankfully, yes. The research outlines a way to fight physics with physics. We can use specific mechanical restoration methods to reverse this contraction, but it requires a two-pronged approach. First, you have to carefully apply heat again to push the material back past that viscoelastic softening threshold. Then, and this is crucial, you have to apply mechanical tension. You have to physically stretch the footwear back out while it's soft to restore its original dimensions. You're basically repeating the manufacturing process yourself, manually stretching those polymer chains back into their ordered, wearable shape, and letting them cool and set.
It is genuinely wild how much complex macromolecular science is hiding in a simple, everyday slip-on shoe. We've seen how manufacturing creates internal stress, and how a little solar heat triggers entropic elasticity to radically change an object's entire shape. And honestly, this brilliantly illustrates a much larger concept. Our manufactured world is absolutely full of frozen potential energy. It really makes you wonder, how many other everyday objects around us are holding on to hidden manufacturing stress right now, just waiting for a hot day to reveal their true shape? Keep an eye out and stay curious.